Okay, so let's wrap up electric fields. This is called this part two. Part three, actually, part three. So part one, we talked about what an electric field is and what it looks like. So we talked about like the patterns they produce. In part two, we introduced some equations like Coulomb's law and electric field strength. That's what we did last time. So what we're going to do today is we're going to wrap up by looking at electric fields and voltage. Okay. So this is the section. So what I've done is I've changed some of the questions. Again, that way we're not doing the same questions as there were in version 1 of this document. Okay. So if you remember, talked about what an electric field is. It's a force that's generated by some sort of a charge, some points or point charge that generates electric force on other charged particles. And it was, if you remember, it's measured in newtons per coulomb. Okay. And what we're going to do today is we're going to introduce electrical potential energy. And what does that have to do with voltage? If you remember last time when we talked about gravitational potential energy, you learned in grade 11 that you know how to measure change in potential energy. When if you're taking an object, lifting it, it'll increase in potential energy. As you bring it closer to the surface, it decreases potential energy. First off, can everyone see my screen before we move on? We okay with my?
Yeah,
we good?
see it.
Okay, good.
Yeah,
okay,
we're
good.
good, sir.
All right, good. Okay, so electrical potential energy is it's same way. You can actually calculate it in a similar way as we did with gravitational potential energy. In grade 11, we talked about calculating it as a function of, if you remember, mg delta h. But in the previous unit, we were able to derive an equation for gravitational potential energy. Sorry. You never get the hang of why it does that. Okay. Last unit, we worked out how to derive an equation as a function of g m1 m2 over r. There's a similar, because if you remember the universal law of and that came from the universal law of gravitation, which, if you recall, was g m1 m2 over r squared. And when we started doing calculations in this unit, we looked at the electric force, due to Coulomb's law, right? Which was K Q1 Q2 over R squared. And if I compare these two equations, you'll notice that they're it's the same form, right? So it would stand to reason that you can derive an equation, an equation for the amount of energy, as we did with when we looked at the previous unit. The amount of gravitational potential energy we derived as gm1 m2 over r. We can do the same thing for electrical potential energy. We can derive this equation and get an equation for energy as a function of kq1 q2 over r. And if you notice, these two equations have the same form. Now, this will allow us then to calculate the energy of a charge at different points, and we'll use that later on when we do some calculations. We can also use this then to define voltage, because voltage is defined as the amount of energy per unit charge. So we can define voltage, because it's per unit charge, that would be basically dividing this equation by some charge, which means you're left with this. This is the formula for voltage, which is represented by some point charge we'll call Q1. This will, if you remember what voltage is, the unit for volts from last year is joules per coulomb, and which makes sense because the previous formula is a way to calculate energy, which we know is joules. So now we're just simply dividing by a charge. So that gives us the unit joules per coulomb. So this is how you would derive the voltage. So we can go from Coulomb's law, which is here, to an equation for electrical potential energy. And then we can convert that into an equation for voltage. And we'll be using some of these concepts today, okay? Any questions so far? So again, here's your voltage, energy per unit charge, joules per coulomb. Okay, so you can see it's defined here again. So we can also define then voltage as simply, because if you remember from last year, we know that joules can be derived as a force times a distance, right? So if you look at this equation, another way to get voltage is the electric force times the distance over Q. Another way to derive it. So we're going to use some of these concepts today when we do some of these calculations. You can see that there are other derivations that we'll be using. Some of these relate to the previous unit. So these are going to come up. Here's an interesting one. Voltage is defined as the electric field strength times the distance. So let's see the connection between these two equations, between this and the previous one, where we define voltage as energy per unit of charge. If you remember, the electric field, the unit for that is newtons per coulomb. All right. Now, if we multiply that by the distance, well, that's force. Force times distance is joules. So this will give us joules per coulomb. So we can see that this equation, is another way to derive voltage. Okay. But we can also then just rearrange this equation and say that the electric field then would be a function of the voltage divided by the distance. So that would be basically, and distance being meters. So we can, in this case, we can measure the electric field not only in newtons per coulomb, we can also express it as volts per meter. These two are equivalent, volts per meter and newtons per coulomb, okay? I'm just mentioning this because these things are going to come up in these calculations that we're going to be doing today. All right. Any questions so far? Okay. So let's look at a first question here. Spark plug. Does anyone know what a spark plug is? What it's used for? Ever seen them?
It's in the car, I guess.
Yeah, it is. Yeah, any combustion engine would have a spark,
yes.
would have a spark plug. So if I was to Google spark plug, oops, not Sark Club, spark plug. This is what they look like. Okay, so they look something like this. All right. If you notice, there's a little gap right here. So if I was to just, for instance, click on one of these images, you'll see there's a little gap here. Okay, so there'll be, in this little gap, there'll be an electrical discharge. And that electrical discharge would then ignite some sort of a fuel. So in this question here, we're looking at the gap of the spark plug. Again, the gap being this little area here, which is, it's about 1 millimeter. So I think it's there's a bit of variation with the distance, but I'm going to say it's about 1 millimeter. So the question is, what is the electric field strength generated by that spark plug if it receives, let's say, 40,000 volts of electricity? Okay, so from the previous example, we said the electric field is, we can express it as a force over charge, right? Newtons per coulomb. But we also said we can express it as voltage per meter. So in this case, it would make sense to say that we can express the electric field of the generated by the spark plug as the voltage over that distance. So that would be 40,000 volts over the distance. Now, 1 millimeter would be, it have to be expressed in meters. So that would be 0.001 meters. So that would give you an electric field strength of, is it 4 million, I believe? Volts per meter. Or is it 40 million? I have to add, wait, 1, 2, 3, 4, 5, 6, 7. I have to add one more zero, sorry. 40 million volts per meter. Okay. Any questions about example number 6? None? Okay. All right. So let's move on to number 7. Let's look at a scenario with a lightning bolt. Okay. So I was actually trying to look up the voltage generated by a lightning bolt. I was surprised to get a lot of variation when you look up some stuff. And so I'm going to go with this, I guess, most consistent result that I got was the voltage of a lightning bolt is about 1 billion volts. Well, if you look up, you get like a wide range of answers. So I'm going to go with this one. So we'll say that the average voltage of a lightning bolt is about 1 billion volts. Okay. Now, the electric field. So the way lightning works is no different than the way you get static electricity. You have to get what's called a buildup of charge. So what happens is you'll have a charge imbalance between the ground and the cloud. And I think the cloud accumulates negative charges on the bottom, if I remember correctly. And that induces the ground to become positive. So you get basically an electric field that's set up that is, well, first off, there's always an electric field in the air, but it's very, very weak. You don't really notice it. But before a lightning strike, there's a significant buildup of charge. So it'd be like almost like, you know, 2 parallel plates where they have, you know, opposite charge. The electric field strength can reach about 200,000 newtons per coulomb. And then it's so large that it will create a discharge of lightning to, you know, restore the balance, to get an equilibrium back. Okay, and the electric field strength in this case is about 200,000 newtons per coulomb. All right, so what's the voltage? Well, there's 2 parts to this question. There's the voltage and then there's the energy, all right? So let's do the voltage first. Sorry, we have the voltage. I must be asking for something else then. Did I not? You know what? I changed this question, ladies. Oh. Okay. Okay, so I had to restart my computer. It did not save the edit that I made. Oh, darn. Okay, the question, okay, we're gonna do the energy. Oh man, this question, I had changed it and it didn't save the change. And I think what I did, dang. We're supposed to find the voltage in this case. But the voltage is produced here. All right, so this was not supposed to be. I had changed this, but it didn't save my change. Okay. And there was a second part to this question, which was in a lightning strike, there's 15 coulombs of charge. So the amount of charge in the lightning strike is 15 coulombs of charge. I think that's what I changed the question to, if I remember correctly. So yeah, so we're going to determine the voltage. Well, the answer is there. It should end up being a billion. Okay, so remember we defined. So we do the voltage first. The voltage, the electric field strength was defined as the voltage as volts per meter, right? Voltage over distance. So we can then rearrange that to say that the voltage is the electric field strength times the distance in meters. So in that case, it would be 20,000 newtons per coulomb times the distance of 5 kilometers, but that has to be in meters. So that would be 5,000 meters. And if we do that, we should get 1 billion volts. Okay. Unfortunately, like I said, didn't save the edit. So we were supposed to find the voltage, not have it as part of our question. Okay, sorry about that. Any questions about that part? Okay, so then the second part of the question is, if the lightning strike produces 15 coulombs of charge, the question is, how much energy then would be discharged by this lightning bolt? So if we think about voltage, voltage is joules per coulomb. So if we arrange that, we can say that the amount of energy would be the voltage times the charge, right? Because this is your voltage, this is your charge, and this is your energy. So the amount of energy released from this lightning strike would be the voltage of the lightning strike, which is 1 billion, or 10 to the 9 volts, times the amount of charge, which is 15. So then that would give you, what would that be? 1.5 times 10 to the 10 joules. Okay. Does that make sense? Let me just double check the numbers, see if they all make sense. Okay. Seems good. Just double checking the math, make sure everything's good. Okay, that's good. Okay, that's good. Okay, all right, let's move on to the next question then. Okay, number 8, we're going to calculate the electrical potential energy of an electron at a distance of 10 millimeters from a +1 microcoulomb point charge. And then the second part of the question is, what is the potential difference or voltage of the actual point charge itself? Okay, so for the first part, we could use the equation for electrical potential energy. If you recall, we defined it as K Q1 Q2 over R. So then that would be 9 times 10 to the 9. That's constant, times Q1. So Q1 we'll say is the point charge. So that would be 10 to the -6. Remember, microcoulomb is 10 to the -6. times the other charge. This is an electron, so the electron is 1.6 times 10 to the negative 19. Okay. Over the distance. So distance is 10 millimeters. 10 millimeters is 1 centimeter, or 0.01 meter. That would give you 1.4 approximately times 10 to the minus 13 joules. Okay. That's the first part, the electrical potential energy. The voltage, if you remember, the voltage was calculated as K times the charge of the point source in this case, which would be this one, over R. So the voltage generated by this point charge would be 9 times 10 to the 9 times the point charge over the distance to the electron, which is 0.01, which would be about 9 times 10 to the 5 joules per coulomb, or volts, right? So the joule per coulomb is a volt. Okay, any questions about number 8? Nothing? Kids fall asleep?
Sir,
Yeah.
sorry, can you also please, because even in the second version, the questions for the voltage are different. Like they are like the first version.
Yeah, I'm gonna change it. I'm gonna update this and put it up, okay?
Thank you.
I don't know what, my computer crashed. Didn't crash actually. The something happened. It keeps kicking me out of the Wi-Fi. It won't let me go back on unless I restart my computer. I must have forgotten to save the update on my dock, so I will. I'll change it and I'll put it up.
Okay, thank you.
Okay, no problem. Okay, so let's do the last question, and then that's it. All right, number 9. So this is an electron that's going to jump from one side of a plate to another side of a plate. So this could be like a scenario in like a cathode ray tube. So a cathode ray tube is an old piece of tech where you could have an electron that's shot out of one end of the tube, and it would travel in the tube to the other end as like a beam. So let's say that this one end would be the negative end. Let's call it the negative end. The other end would be the positive end, and the distance is 50 centimeters. Okay. All right. So let's say the electric field strength between the two parallel plates is about 2,000 newtons per coulomb. But remember, you can express that also as volts per meter, right? Because we said that they are equivalent. All right, so we're going to do 4 things. We're going to calculate the voltage between the plates. We're going to do the force on an electron, because these beams are really just little electrons flying through the cathode ray tube. We are going to calculate the change in potential energy, and then we are going to calculate the speed of the electron. Okay, so let's do A first. So in A, we have the voltage between the two plates. So remember, we could do the electric field can be defined also as volts, voltage per distance. So we could say that the voltage is the electric field times the distance. So then we could say that the voltage would be the electric field, 2,000 volts per meter, remember, because these are equivalent, times the distance in meters. would give us a voltage of about 1,000 volts. Okay, so there's 1,000 volts running through this cathode ray tube. All right, that's A. Then we have B. B is the force on the electron. So if I look at my electric field strength again, so I know my electric field strength is 2,000 newtons per coulomb. So obviously, if I look at this, I can say that if I multiply the electric field times the charge, then that would be the force, right? So I can say that the force would be the electric field, 2,000 newtons per coulomb, times the charge of the electron, which we know is 1.6 times 10 to the negative 19 coulombs. You can see then that cancels out, and that would give you a force of about 3.2 times 10 to the minus 16 newtons. Okay. Good thing about like a lot of this stuff in electricity is, let's say you forget the formulas, the units kind of tell you, how to derive the equations. This equation, we actually saw that one last unit. Sorry, not last unit. Last time we met, part 2. But even if you forgot the equation, you can just tell by looking at the unit of the electric field how we can extract force from that, right? Okay, so look at C. C. We're going to look at the change in potential energy. Okay, so we can go back to voltage. We know voltage is joules per coulomb, right? So again, we can look at something and derive the equation. We know volts is joules per coulomb. So if I multiply that by the charge of the electron, which I know is in C, right? Then the units, the coulombs will cancel out, and I'll be left with energy. So I can say voltage times Q would be the energy acquired by the electron as it flies through the cathode ray tube. So then the amount of energy would be the voltage, which we just said was 1,000 volts. 1,000 volts is the same as 1,000 joules per coulomb, times the charge of the electron, the charge of the electron, which is 1.6 times 10 to the minus 19 coulombs. And that would give us an amount of energy that would be about let me just move this bar out of the way. 1.6 times 10 to the minus 16 joules. Okay, so that's how much energy the electron would gain as it's moving towards the positive side. Now, it would gain that in terms of kinetic energy. In terms of potential energy, it would be losing that, because we said last time we defined that potential energy, PE, if you remember, decreases when it goes in the direction that it wants to go, right? So like object falling to the ground, its potential energy would decrease because it wants to fall to the ground. And the potential energy would increase in the opposite direction. In this case, the electron wants to go to the positive side, so its potential energy is going to decrease, but we know that the energy is going to get converted into kinetic energy. So this energy then becomes kinetic energy. So we're going to use that then to figure out the speed of the electron. So if you recall, the kinetic energy is 1/2 mv squared, and that's going to equal the energy gained by the electron as it's heading towards the positive plate, which we defined as calculated as 1.6 times 10 to the minus 16 joules. So if we do some rearranging, so V would be 2 times 1.6 times 10 to the negative 16 divided by the mass of the electron, which is about 9 times 10 to the negative 31. And we square root that, we will get the velocity of the electron. Works out to about 2.7 times 10 to the 7 meters per second. Okay?